There we go. Now we're recording. All right. So first off, it's Monday. So the two parts, I briefly mentioned this last week, but I want to make sure we're all clear on this. So part one, 14 multiple choice questions. You can take that part anytime from 8 a.m. to 6 p.m. Now, when I say 6 p.m., really it means 5 p.m. And that means is that the test itself is physically available from 8 to 6, but it'll disappear at 6. So if you start at 5:30, you're only going to have half an hour to do it. So please don't start any later than 5 or you'll lose time. So you have a full 60 minutes to do it. Most people last quarter, when we did a very similar test, took about half an hour. That was about the average. So, take your time, read the questions. Just because it's multiple choice doesn't mean it's necessarily really trivial. Because there'll be multiple answers that look very similar and you need to be able to distinguish them. Now, and I'll go over the topics of what will be in that, but just be aware. So you'll get that done anytime during the day. And generally we will have a Zoom room available where an instructor is available anytime during that 8 to 6 p.m. or so that if you have questions, it may not be me, but it'll be someone. And if something comes up and you can't get hold of them, then I should be available all day Monday, also just working. So you can shoot me a quick email or something. So in terms of point breakdown, now these points aren't the same points as what's on Canvas. Obviously, the final's worth 40% of your grade. So what I will do is say you get 80 out of 100 on this. I'll multiply that by 0.8 times 40, which is 30, what is that? Yeah, 32. So you get 32 points towards your 100 points total for the class. So anyway, that's how it'll be graded. But so that's 25 points. And then we have part two. Now part two will be similar to the final, similar to the midterm in that you'll have 3 calculation type questions and you'll have each one will be on a different topic from a different chapter. And so you can figure that out of the 3 questions, we took a question from possibly from chapter 3, one from 5/9, one from 6, and one from 8. So you won't have 2 questions from any one chapter. You'll have a chapter on friction, potentially. You'll have a chapter on a frame, machine, or a truss, potentially. You'll have a moment of inertia problem, potentially, and then you may have a moment problem, okay? So that's what to expect. Now that you have from 7:10 to 8:45, and that will be live with me. So everyone will just like the midterm, everyone will have their cameras on, not so I can glare at you, but just, so I'll have my camera on too. And if you have questions, you can either send me a private chat through Zoom, or you can just ask it out loud. And if it's something I can answer, I will. If it's specific to your answer, I prefer you sent me a chat. That's easier because obviously it's not a group exam. But the other thing is, if there's a question you think is a clarification, please ask it, because if it is, then I'll clarify for everyone. And I like this part because in being live with you during the test, because if you have any questions, you can ask them in real time and keep moving on. So that's that. So any questions on this so far? Okay, good. All right, so the topics of the test. So chapter 2, no specific questions from this chapter. Remember that this chapter was really doing vector math and learning how to, I would say most of it was review, but doing things where you just take force and you convert it into its IJK components. So there won't be anything specific, but as you know, we use that material later on in the quarter. So chapter 3, the 3 main topics from chapter 3 were moment about a point, moment about a line, and the idea of equivalent force couple systems. And what falls into that also are equivalent couple systems. And so if there's a question on the test, and so when you think of this chapter, there's a lot of just understanding the process. The math itself isn't really difficult, as you found throughout statics, but understanding the specific process. And this is where you really want to pay attention when you're doing these multiple choice questions. So for example, a good multiple choice question might be to show you a diagram and say you're trying to find the moment about point B, and your force vector goes from C to D. And then it may ask you, where should your R vector go? What point should your R vector go between? And so if you think about that, and let's go to what we're talking about, you remember that whenever you're doing a moment about a point, you always go from the point to the force. And I know it sounds trivial and that it seems like I'm beating a dead horse, but I was really surprised at how many people kind of missed that on, they missed it on midterm. And so it's just something you want to be aware of, and because that's a question in the multiple choice, and it'd be very easy to say, oh, get ahead of yourself and say, oh, well, it's going to, as long as it's going from the point of the moment to the point of the force, it doesn't matter which direction, but it does. It has to go from the point to the force. And it doesn't matter where on the force it goes to. And this same logic goes with a line, anywhere on the line to anywhere on the force. Okay, so burn that into your head. And also remember that when you have a moment about a line, that is always a scalar. You have a moment about a point, that is always a vector. Okay, so don't make that mistake. And so the multiple choice are really aimed at fundamental knowledge of the stuff you've covered. So if you've been paying attention, you understand the homework, then you should do fine on the multiple choice. But it is tricky. If you just look at it quickly and rush through it, then you will get bitten. So just be careful. So I put up a few examples. These are ones that you may want to look at. These are out of your book. These would be good examples that would be relevant to the information that I'm discussing right now. Okay. So other thing with force couples, so that was the second part of chapter 3. What is a force couples equivalent? So remember with that, there's also a question on the on the midterm about that. It said where you want to always identify the direction of the force of the tension vector. That's of course the first thing you do, and that's pretty easy. But you want to be able to, again, identifying the correct R vector going from point A to B. And on the midterm, the problem is a little tricky because what I did is I also added an additional moment. So and a force. So not only did you have to take two forces and cross product them with the R vector, but you also needed to convert a moment to a vector and then add that in the final moment. Okay. So that type of problem that would be, if we were to give you a problem on the final, that would be about the equivalent of difficulty. So just be aware, and really if you follow it like a recipe, it's really not that hard. You just gather all your forces, you cross product them, R cross F to get the moments, and then you add all the moments together that you have, and you have in the end two answers, a moment and a force. So I put up a couple of examples here, 3.9497 and 3.120. I believe a couple of those, if not all, I've already done in the lectures. And so I would just go back and review them. I would say I would suggest in terms of studying, I wouldn't do a lot of chapter 3 problems to completion. It's not because you probably won't see that as a calculation. What I would look at more is just the concepts. How do you solve them? Okay, if you have a solid understanding of that, you should be fine. Okay, so chapter 4, that was a 3D equilibrium. And I mean, there's not a lot I can say about it. It's a 3D equilibrium. And if you look at the midterm, that's an example of the type of problem. If we were to give you a 3D equilibrium, it would probably not be, it'd be a setup only, kind of like what we did on the midterm. But if there was a multiple choice question, there might be something just simply asking you, what are the R cross F vectors that are appropriate. So as you recall, when we did 3D equilibrium, we had generally you have one point that had multiple unknowns, and you generally take a moment about that point, and then you create your matrix of different cross products and set them all equal to 0 to solve. So I would, if I were you, I would review the midterm example. And again, if you haven't looked, the solutions for everything, the only solution that's not up there, which will be up there shortly, is the last quiz, quiz number 8, but all the homeworks, all the other quizzes, and the midterm solutions are all posted on Canvas. So be sure you want to look at them, they're there for you. Unfortunately, I can't post past finals. That's a department policy. Otherwise, I would. So I'm trying to do the next best thing by showing you problems that are pretty much the same as what you'll see. So that's chapter 4. Again, just look at the examples, you should be fine. You have the advantage of an open note test. Normally we have a closed note test, but I would highly recommend writing down the different things on one sheet of paper, because not only will it help you understand the material better, but it'll be like an easy reference. You're not gonna have time on the test to go back in the book and look at examples and study. It's just gonna go too quickly. Okay, so chapter 5 and 9, locate a centroid of 2D composite geometry. So we did centroids of 3D, that won't be on it. Usually we combine this chapter into a question. So most likely what you'll see is a question or an image like I've shown you in these two. It'll be a composite with simple shapes, triangles, circles, and squares. And you will be either asked to find the centroid of the object, and which you guys can do. And then you'll probably be asked to find the moment of inertia about that, either the X bar or the Y bar. And so depending on which one, usually we don't do both because it's just time consuming. So the thing I want to emphasize on doing these is they are, they're kind of a recipe, as you saw with centroids. But when you do the parallel axis theorem, just remember to always use the centroid moment of inertia. So for example, if you're on this lower problem here with the triangle, if say you're trying to take the moment about the x-axis without worrying about the centroid, you're not going to go, your distance would never be from the x-axis to the base of the triangle. It would be from the x-axis to the centroid of the triangle, and in which case you would then use 136 BH cubed. Now, in some cases, it may be possible that by luck of the draw that it works to do 112 BH cubed, which is what the moment of inertia is about the base, and then use the distance to the base, but that's coincidental. So you're gambling if you do that. Most likely you're going to get it wrong. So does everyone understand that? Always going to the centroid. So as long as you follow that, you'll be fine. So what I would say is, if you get a problem like this, high probability, and go ahead, identify the centroids of each piece that you divide it into, and then write down the distances from that centroid to the global centroid. And the more information you put down, the more partial credit I'll give you. So if you write everything down, if you write the D correct, and you write the correct equation showing me that you're taking it from the centroid, even if you get the answer incorrect, you're not going to lose more than a couple of points, because I'm not here to make sure you did every math equation perfect. I'm really focused on whether you understand the material. Okay, so that's chapters 5 and 9. So chapter 6, we just finished with trusses, zero force members. Remember, with trusses, you have both method of joints, method of sections. You've had a few practice problems. Here's a few more that you can look at, but again, understanding trusses, I don't think it's most of the time, any trusses that are given are fairly simple. They don't have really gnarly geometry like some of the homework problems. because we're not, we're not looking for you to spend half an hour on trade. We just want you to understand the topic. So you'll find that the way that we approach the final is that we're not looking to give you those problems that are at the end of the chapter that are always really difficult. We're looking to give you more middle of the road, mainstream problems that just show that you have competence in the topic, because that way I feel comfortable giving you a grade, and then that way you move on, you take dynamics or C204, and you'll thrive in those classes instead of getting hammered. Okay, so then we have frames. With frames, I recommend is find the external reactions first. And so usually a frame will be held by 2 points. So pick one point that has an X and Y component, sum the moments about that point, figure out what the other reaction is, sum forces in X and Y, and then you'll get those. Then start taking your frame apart and look at the different pieces of the frame and read the question too, because sometimes you only need to find one or two of the forces or one or two of the points in their forces. So you're not going to worry about finding everything. All right. So another thing is, remember, be sure you understand the two force members. So if there's any kind of a force applied to a member, it can't be a two force member. So if it has a moment on it or another external force or a reaction for that matter, it can't be a two force member. So therefore you don't have that knowledge of the exact direction in which the the forces are going. You can't just assume if it's a 3, 4, 5 triangle that the forces in the X and the Y are in the 3 or the 4. All right, so there's a couple of examples, 6.7, 6.83, 6.105. So I bolded 1.05 because I wanted to go over that one real quick. And let me pull it up here. And I don't think, I should have put the picture in here. Bear with me for a second and I'll get that image. Put that in there. Bear with me for a second. I'm gonna put the image in this. Oh, you're wicked. All right, the thing's being a butt. So my laptop's not cooperating. What I'll do instead is I'll just draw it for you. It's pretty simple drawing, but I would like to go over it just because I think it's a good example of a frame, like the one I saw that you might see on the test. Maybe you might see. Of course, nothing's absolute, right? Sorry, my document is not. Boy, it's just one of those days. There we go. Now it's beginning. Sorry about that delay. Technology grand. All right. Just draw this real quick. Okay, so let me draw the problem real quick. It's so what we have is a Remember, it looks like this. Okay, so my cryptic drawing, you have this frame. It's connected a pin here at D, a pin here at E, a pin here at B. And then there's this hinge, and not hinge, it's kind of a little indent like that, and then it's sitting on a ball. So we know that you just have a single reaction H going up. And we know that over here at G, we have Gy and we have Gx. And then we have these two 12 kilonewton forces. Actually, this is 6, sorry. This is a 6 kilonewton force here. And so what we're asked to find are the forces acting on member DABC at B and D. So DABC, so here's DABC. And so what it turns out is that this and this are this is a separate piece, and then DABC is one connected piece. So it's pinned here at B and it's pinned here at D. Okay. So we want to find basically what are dx, dy, and what are bx and by. Okay. So this isn't a difficult problem. It's just, but when you look at the final, you want to, if you get a frame and you're not sure, well, what do I do with it? Where do I start? This is what I want you to remember is, okay, well, first thing we want to do is, because we have two reactions here and only one here, we know we can sum the moments about G to get H. So if I do that, if I sum the moments about G 0, then I know that, and I haven't dimensioned it for you very well at all, actually, 0.6. If you have your book, this is problem 105. So if you open your book to 105, you'll see the dimensions. So the main thing is just to focus right now. And let me just put those in, because those make a big difference. 0.5, 0.5. This distance here is 0.6. That distance there is 0.2. And this distance out here is 0.4. All right. So we know if we sum the moments about G, we can get H times 0.6 minus 12 kilonewtons times 1 meter, and then minus 6 kilonewtons times 0.5 meters, and that all equals 0. Okay, so we end up with getting H is equal to 25 kilonewtons, and we know the direction, 25 kilonewtons, and that's going up. Okay, so then we ask ourselves, well, do we need to know G? And so the question is, we don't know yet. Now, we could easily figure out G, and normally I say go ahead and do it, because we can see that if it's 25 kilonewtons going up, that means that Gy, since this is Hy, has to be 25 kilonewtons going down. And Gx has to be 18 kilonewtons going to the left. So that's just simply looking at the whole thing, summing the forces in the X, summing the forces in the Y. So now that we have that, what we can do is we can look at this piece here. Now, the reason I'm looking at this piece here is because I know this, and I don't know that, and I don't know that. But but you might be able to see that if I take this piece off here, it looks like this. Okay, make sure you guys can see that. So if I draw that, I know that I have, and again, I don't know the directions of by or bx. I'm just drawing them in. I have by, bx. I have ex, and I have ey. And then down here, I have that value I just determined, which is 25 kilonewtons. So if I sum the moments about E in this case, then that eliminates everything but Bx. So if I sum the moments about E, I can find Bx. And so I get Bx. Now, if I look at this, if I'm summing the moments about E, then Bx is going to make a clockwise moment, and so is that. So if I write minus Bx times 0.5, that's the distance between here and here, and then minus the 25 kilonewtons times 0.2.
Hey, Professor, quick question.
Yeah.
You did minus Bx because the assumption was wrong, right? That Bx would point to the right?
My assumption was wrong. That's correct.
Okay, cool.
So I left it there like that just to show you.
But yeah, perfect. I was just double checking that.
Yeah, exactly.
Thank you.
What I end up with then when I solve it is I end up with Bx equal to negative 10. And so if you get a negative anytime when you're doing a moment, that doesn't mean it goes well, in this case, it does go to the left. So I guess that is correct, but it means that I guessed wrong. So I know now I can look at this. I know that Bx has to be going the other way. Now you don't have to go back and change your free body diagram as long as you're aware of that. So what I would do is just write, when you write your answer, because one of the answers we're trying to find is Bx, just write as, you can write it as negative 10 kilonewtons, or you can write it as 10 kilonewtons with an arrow to the left. And that works fine too. All right.
Professor?
Yes.
But the reason you put the minus Bx in the moment is because it was the turning to the right, right?
That's correct, yes. Because the way I wrote it, I had it be making a clockwise moment with E. So you can see that if it's my pencil, the 25 is going to make it go this way, and so is that. So it makes sense that it couldn't be, otherwise it would be free rotating about E, but it can't.
Okay.
It's gone the other way. And after you do these, you'll probably instinctively just look at it and go, well, if 25 is going up, that means Bx can't be going to the right. It has to go to the left. And you'll just figure that out on your own. So after you do it for as many times as I have, it'll stick to you. But okay, so now that we have that, we look at it and say, well, what more do we want to do with this? Well, again, getting back to the original problem, we know that we just need D and B. So if we take this piece apart, then what does that look like? It looks like basically like that, where we don't know where dx and dy are. Sorry, it's getting old. But we know, we still know we have 12 kilonewtons there. And we know that on this piece that we have, which direction is dx gonna go to? It's gonna go to the right. So we know that bx has to be going to this direction, and we know it equals 10 kilonewtons. Because the other piece we found went to the left, and so when we took this piece off of that, we know it has to switch. So it's going to the right. I think that's one of the more trickier parts about frames, is remembering that when you take them apart, if they're connected to another piece, that the other piece has to have the opposite. So now we know that's 10. So you can kind of see where this is going. See, we just need to know what by is, and we just need to know what dx and dy are. But we're pretty much done at this point, because if we sum the moments about d, that's going to give us by, and then we just simply sum the forces and we can get the remainder. Okay, so if we do that, we end up with getting a by equal to 13.75 kilonewtons, and it turns out that it's going up. we end up getting a dx equal to 22 kilonewtons going to the left, and we get a dy equal to 13.75 going down.
Wait, Professor, could you explain that one more time, how you got those?
Oh, sure. So once I have this piece here, I know this. So if I sum the moments about D.
Oh, you sum the moments about D. Okay. Perfect.
Yeah. And then I just have the one unknown. Then I can just solve that.
Awesome.
All right. Does that make sense to everybody? Good.
So if you get down to your target member and you only have 3 unknowns, then you're good.
Yes, you are. You're right.
Okay.
Then you can just sum moment about 1 point and you're done. Unless, one of them's here and not here, right? Well, I guess that goes through that, but you won't see that. We're not going to trick you. So pretty much all the frames break down this way. They're all going to, and so no matter how, we're not going to give you any 9x9 matrix. It's just going to be a fairly simple geometry. Just a look at it, read the problem, and if it's not clear, ask me, and I'll be sure to explain it to you guys. So I don't want any of you to not get the problem because you don't understand the wording. Okay, so that's that one. So let's go back real quick. Where did? Oh, sorry about that. Hold on a sec. All right, there we go. Sorry for it's not as seamless as I'd like to have been. All right. Okay, so we got machines. So then the last one was machines. Machines are pretty much the same process as frames. I would say that you probably if you get a machine, you probably won't be able to. You probably will see it. Well, I guess what I'm saying is it's not going to be any real different in solving than if you did a frame. So what I would do is, if you're still, the difference between machines is mainly what a machine is by definition is something that modifies force. So you saw that we looked at bolt cutters or vice grips, and we looked at toggle clamps and whatnot. And really look at those. You're usually not going to have it with a machine. It's not going to be connected to the outside world, a hand tool, obviously. So what you're looking for are 2 force members that you can exploit. And so I would say that the homework problem that had the toggle clamp where you had to determine the reaction at P, that's a good example. Make sure you understand how that one was done. Look at the examples that I covered in my lecture. So I wouldn't spend a lot of time on it. I just make sure that you understand the process. Okay, and then last is friction. So wedges won't be on the test. So we did cover them. Belt friction will not be on the test, so don't worry about it. Though you'll probably have a general, one of the problems on the part 2 will probably be a general friction type problem, because it falls within those categories. There's basically, you have there's 4 possibilities, right? You have chapter 3, chapter 5.9, chapter 6, or chapter 8. So there's a high probability chance that you'll see a friction. So I want to look at this one. This is a really simple problem, but but as long as you keep in mind with friction that it's, don't get intimidated by it. Just remember that the friction problems are just really about exploiting the fact that the friction force, you're always on the cusp of motion. So you're always looking at something that's going to, can you guys see my slide? Can you see when I shared the screen, is it back again?
Yeah.
Oh, okay, good. Sorry about that. I just want to make sure. So when you look at friction, and let's just walk through this problem because I think it'll make more sense, and I'll narrate it as I go. So let me do this. All right. So we have a ladder, And we're not given much information with this problem. We just have basically a ladder sitting against the wall. And it's what, 6 meters? So it's basically 6 meters up and 2.5 meters down here. All right, so now we know that it's, and so we want to find views of that. All right. Now this was a problem that I put on the homework, and they showed the solution using an angle of repose, which I think is a little confusing. So better way to solve it is just saying that, well, here's point A, here's point B. Now, if we draw the free body diagram for this, we know that it has a uniform, it's a uniform ladder, so there's uniform mass. So we know that the mass, or the weight, we'll say the weight is in the center. We know that we have a normal force A, and we have the friction force A, because the assumption is the ladder is going to do this, it's going to slide out. And so as we'll find is that really where the ladder sits physically is going to determine the coefficient of friction. And this makes sense. I mean, if you've ever, obviously all of you have used a ladder, I hope, but you'll notice that if you put the ladder more towards vertical, then you don't need as much friction to hold it in place, because most of the holding power comes from the normal force. Whereas the more you put the ladder like this, the more likely it is to slide out. And so, and you also usually have friction working on this side. Now, if we add friction to this side, we can solve it. It just gets a little more complicated. But we're, for the final, we're just looking for you to understand it as a fundamental. So since this we assume is a smooth surface, we're just going to write it as NB, or the normal force at B. Now, how are we going to solve this? So we don't know. But we just know it's uniform. So if you don't like having it in variables, then just pick a number. If they don't give it to you, then it means that it's not going to matter in the end. So if I want to just make life simple, just say the weight equals 100 newtons, then I can do that. I know these distances, these are important because, again, depending on where the ladder is, it's going to determine the coefficient of friction. So I can go ahead, and if I want to isolate, I know weight, but I can isolate some variables. I can go ahead and do this, and we'll call that point H out there. So now if I sum the moments about point H, then I eliminate the normal force at B and the normal force at A, and I can solve for the friction force. And so if I do that, what do I get? I have friction force times 6 meters, right? And that's going to be minus 100 newtons. And that's going to be times what? 2.5 meters. Equals 0. So if I take out my calculator and I solve, I get what? 250 divided by 6. 41.7. Is that right? Oh, you know what I did wrong? I'm sorry.
Have to half the distance.
Yes, that's right. Thank you. I just realized that. Yeah, I don't know what I was thinking. That's 1.25. All right. So that changes that. So that comes, basically, this becomes 20.8. There we go. So I know that my friction force at A is 20.8 newtons. And then if I look at this, if I sum the forces in the Y direction, then I can see by inspection that NA equals W, right? That's the only thing I have. So now I know that NA equals 100. And so I know by definition that mu static is just the ratio of FA to NA, and that's why I picked 100 to make it simple. So I know now that if I just move the decimal over 2 places, my my coefficient of static friction is just 20.8 over 100, or 0.208, or 0.21. So in the real world, friction is never reported to more than 2 places. It's just not that accurate. So this is kind of, it's always rounded up. But one of the things with friction is that you're always, when you solve these, you're always going to make sure that you have a good free body diagram where you identify this and this, everything. But the important thing to remember is that if you're just on the cusp of motion, that you always know that this relationship, that friction equals mu static times n. And that's your best friend, because what that does is it relates the force in the x to the force in the y. And so by substitution, you can do that. Now, I have a feeling that on the final, if you get a friction problem, you're going to have to look at your substitution, look at how these different relationships algebraically work with each other. Okay, so I don't want to say
the question.
Yeah, sure.
Sorry to interrupt you.
No, that's all right.
So friction force on the vertical component.
Oh, because that you're told in this problem that the wall is smooth.
Oh, okay. If that was, then finding the AY would be a little bit more complicated, right?
It would actually. And so if you did that, you'd end up with something that looked like this. You'd have, let's say that's your ladder. And in this case, let's just keep the same dimensions. So now we still have normal force A, we have friction force A, we have our weight, we have normal force B, and in this case, we know that the friction force is going to go up because the ladder is going to want to do this. So we have FB. So in that one, there's a whole bunch of steps. But for example, one way to solve this is you could start at A, since they both have 2 unknowns. If we were to sum the moments about A to 0, then we would get what? We'd have weight times 1.25.
And then you'd have normal and friction, right?
B times 6. And then you'd have minus mu static times normal of B times 2.5 equals 0. And see, what I did is this is really FB, but I just put in mu static times NB because that's equivalent to that in this case. So then I end up solving. If I want to, I could solve for this. And if I solve for this, I get 1.25 W because it's by itself, and ends up being, factor that out, ends up being 6 plus 2.5 mu static. So now that.
It's messy.
So it does get a little messy, but then what you end up doing is you can sum the forces in the Y to 0. You end up summing the forces in the X to 0. And then you end up combining terms. And actually in this particular instance, when you combine the terms, because you're going to end up like substituting in an NB where you already have an NB, you end up getting the mu static terms as a square. So this ends up being a quadratic. And then so you just put it in terms of, AX squared plus BX plus C equals 0. And then you solve for your roots. And usually one root is negative, which means it's meaningless, and you pick the other one. So that's more than we'd expect on a test, though. We're not going to give you that on the final.
Okay, sick. Never mind then. Thank you.
Yeah, sure. Okay, so that's pretty much what I wanted to talk about. Sorry, it went a little longer than I thought, but I just wanted to give you kind of an overview. So what questions do you guys have?
Could you just draw like a little example truss and then have us do the zero force members?
Yeah, I can do that.
Just like give us a second to guess before you do it.
Absolutely.
Thank you.
Yeah, actually what I'll do is I'm going to grab one out of the book because they have better drawings than I have.
I also had a general question.
Sure.
I was having trouble finding the friction homework you posted. Where are those practice?
Oh, they're under, let me go. I'll go into Canvas right now.
Yo, I had that question too. I found it in office hours. It's in the expectations. It's like week 9 expectations or whatever.
So, in the modules,
Okay.
it's week 1, 2, 3, all the way up to 9. If you go into week 9 module, it should be in there. And the reason I didn't put it in the assignments is because it's not graded. So it would have screwed up with the assignment because everything in there has to have a point value. I guess I could have given it 1 point, but that's
Okay, I found.
Did you find it? Good. Yeah.
Thank you.
Sure, no problem. So in terms of there's lots of well, I could let me just make something up. I'm not finding something I like. Several other static stuff too. Anyway, let's just make something up. So
Professor, could I get a recenter while you're drawing? Just so I can keep up with you.
oh, is it not recentered? Is it? There we go. Thank you. Okay, so there's that. So go ahead and look at it and pick out what you think in terms of, you just this is a B. Just label them by what number you think they are. So identify what you think they are. So who wants to, does anyone see one?
I mean, for me, the GH and FH look like zero force members
Why do you think that?
because they're not collinear and there doesn't seem to be a load applied to either of them.
That's correct. That's good. Yes, you're right. So because FH and GH are hanging out here, and we get complacent because usually we put the supports on the ends. But you're right. So this doesn't need to be there. I mean, in this loading situation, these don't support anything. So good. What else?
Would DE be one of them?
Yes, that's correct. So DE, and that's a pretty clear. It's hopefully one you'll see. All of you saw right away, and you'll see those quite often where you have, again, you have 1, 2, 3 members meeting at a point. 2 are collinear, meaning the straight line. The third is not. Therefore, the third must be. Even though down here you have 1, 2, 3, 4, 5, which you wouldn't be able to know from that. It has to be work on both ends. So the only way this could be is if I say I applied a force there, then it would, but we didn't. So
what about FG?
FG. So FG has a support down that end. So that's why FG isn't. And then on this end, it has 1, 2, 3, 4 plus a force.
Okay. So we can't tell from that end.
No. So what happens with FG is, if you think about it, FG would end up like this. This part would end up essentially like this. If we were to draw the G, it would be like that. So when we went ahead and calculated, and this might be statically determined because I have two of those I haven't checked, but effectively you can see that this, whatever the X or Y reaction was, would have to be the same. So this would be, would be the same as that, and whatever the Y reaction was on this would have to be this. Okay.
Okay. Right.
And then what about, well, there's one more.
I would guess EG.
EG?
Yeah, but that's connected to a support.
Yeah, it's connected to support. So what about this one?
Oh, because there's nothing at the bottom.
Yeah, there's nothing at the bottom. So
Isn't it directly connected to a external force though?
it doesn't matter. It has to be on both sides. So what ends up happening in this one is that if you were to go through and calculate it, even if you didn't know it was zero force, you'd end up that the force would be carried by this, this, and this. And this would have to be zero, because what would happen is when you, let's say you started in this corner and you'd find that there was a force, let's say this is in compression and this is in tension, then that would be in tension too. And when you looked at C, what would you have? You'd have C, you'd have something doing that, you'd have that doing that.
Right, just the X.
So when you sum the forces in the Y, what do you have? You have nothing. So BC zero.
Okay, cool. Thank you.
Sure.
Whoa. Okay. Is that it?
That's it. That's all there are. So there's a couple examples in your book, and you also, if you Google zero force members, there's tons that are just images. So you can just download an image and just look at it. And but I mean, they're really not that. They're not meant to be that complicated. We're not going to try to trick you with them. We're not going to give you something crazy. So as long as you reckon, and this has the both. You have two of them, and they're not collinear, therefore they're zero. You have 3, 2 are collinear, therefore the third is zero. As soon as you have more than that, if you have 4, then you can't know without calculating. And if you have a reaction or a force, you can't know either. Doesn't mean it can't exist. It just means you can't rule it out instantly from looking at it.
So it's the odd man out if they're collinear and there's 3 of them. And then if there's 2 and they're not collinear, then they're both 0.
That's correct.
I don't know why. It just doesn't stick in my head.
Oh, it will. It will.
That sounds so ominous.
Huh. Well, no,
I'm scared now.
It's not meant to be horrible. So anyway.
Okay.
Any other questions you guys got?
Can we do a problem from chapter 3, like similar to the one on the midterm?
You mean like a moment, force couple system, like that?
Yeah.
Yeah, that's fine. Sure. So let's see. There's one that's good. Actually, I think I gave this one on a test a long time ago, but let me pull it up. I could create one, but they all pretty much use the same thing. Yeah, so this one here. So let me show it to you. I'll draw it, but it's problem 3.97 if you have your text. Let me go ahead and draw it real quick for you.
Can you adjust your camera?
Yeah, sorry. I just you won't see much until let me draw this, make it somewhat easy to see. let me turn I'll turn the magnifying back on. Oops. There we go. All right, so there's that. So we know, let's make it a little different. We'll have a moment going from here to there. All right, so we'll give that, let's just say that's 70 Newton meters. Okay, and then we label all the points. So we have, this is point A. This is A, B, C, D, I guess G's in the corner. I know my ABCs. All right. And let's just draw that from, you can do it from here to here, halfway. So we'll say, and so I know you guys can find forces, so I'm just going to give this force a value. So here's my x-axis, y-axis. So normally in this problem, you're given this location and that location, and you have to find the unit vector and whatnot. So for simplicity, I'm just going to say that this vector, it's 25i minus 20j and plus 35k. All right, so we'll make that. And so we're at this location here, and for our dimensions, we're going to say that this is 28. Yeah, 28. So this whole width is 28, and this whole length is 45, and the height is 14. Okay, I think that's everything. All right. Okay, so a problem like this would usually, it would give you, like in the book, it might give you, say, given, we'll call this P. So given force at P, and maybe it just gives you 46 pounds and then expects you to find it, but I know you guys can do that. So given force at P, determine the, and then force at P and let's say and moment 70 Newton meters as shown. Determine the force couple, the equivalent, sorry, I always say equivalent, sorry, so small. Determine the equivalent force couple system at H. So let's go to H, okay? So we want to think about how are we going to solve that? So again, what we're doing is we're going to move this force over to H, and we're going to add a moment that corresponds to it. And we also have to account for this 70 Newton meter force. So our final answer is going to consist of a force. Now because there's no other force, there's just one force, we're going to just put it down. Now you may recall on the midterm, what I had done is I gave you two forces. So in the midterm, you needed to add those together, and that would have been your final answer. So first off, we know our force is just 25.0i minus 20.0j plus 35.0k. All right. And now we want to figure out what our moment is. So now we know our moment, let's look at the 70 Newton meters. So we'll call that moment 1. And that's going to be 70. And then it's going to, let's got to figure out what is our unit vector. So our unit vector is going to be minus 45i, right? And plus 0j plus 28k. All right. So what is that? So 45 squared plus 28 squared is 53. So We know that's over 53. So what we do is we go ahead and we multiply 70 by negative 45/53. And we get 59.4. So that equals 59.4 negative I plus 0j, and then 28. And that gives me basically 37.0 Newton meters. So far, so good. Everyone see what I did? So all I did was convert this to a vector. That's it. So then now I need to find my R vector. R going from, R goes from B, from B to D. And I'm sorry, it goes from H to B. So we want to go from the location that our new location to B. That's what's important. We're going to go from here to here. So in that case, we know that R is just going to equal 45I plus 14J and minus 28K. And the only thing is, I'm sorry, I went to B, but I really wanted to go to here. That's where the force is. Sorry about that. I was thinking something else. So I'm really going to P. So this is basically P relative to H. That's how it should be written at. So I'm going from H to P. So I got these right. I didn't get the Z correct because we're halfway. So this should be 14. Sorry about that. So happens when I make them up on the fly. So there we go. So now we're pretty much, we have R, we have F. So now we just need to do our moment. And so we just do R cross F. And so what we do is we set it up. We have 45, 14, negative 14. And then we have our 25, negative 20, 35. Do your cross product, we get moment, we'll call 2. And then you add that to this, and that's your final answer. Make sense?
Yep.
All right. Good. Well, we lost a few. So any other questions you guys have? Okay. Well, what I'll do is I will post this. So if you missed anything, and if you have any questions over the weekend, feel free to shoot me an email. I'll be around. So I don't think I'll have a formal Zoom, but if there's something you want to discuss, send me an email and we'll figure it out. Okay.
Thank you.
All right, you guys. Well, good luck. I will see you on Monday if I don't talk to you sooner. But again, email if you have questions, and good luck on the test, and good luck on your other finals too. It's been a good quarter.
I have a question. What do you have written
Sure.
below the cross? Sorry, or that? Okay, I see. Thank you.
Oh, down here, yeah, that just says moment too. So once you get that, that's your second moment. You just want to add it to this one here, and have your total. That's all.
Sounds good.
All right. Okay, you guys. You have a good day, and we'll see you soon.
Wait, is our final on Monday?
Yes, it is.
Okay.
So,
And then-
did you get here late?
No, I was just confused on. This was the only class I didn't know what my final was. But so it's just.
Yeah, no,
it's
it was on the syllabus at the beginning of the quarter, just to maybe
Yeah,
Dave, you didn't
I was
see.
gonna check it, but since I was like in here, I was.
Oh yeah, no. Well, here, let me show you the page. Let me go back to it.
Mhm.
If we look at,
Okay.
see this is so. Remember part 1, 14 multiple choice questions. That's
Mhm.
6. So meaning you have basically you have a 60. I should have wrote that in there, but you have 60 minutes to take it. So you can take it anytime starting at 8. You don't want to take it any later than 5 because it closes at 6.
Okay.
It's 25 points, and then part 2 will be at 7:10 to 8:45 p.m. on Monday, and then
Okay.
25 points. Okay.
Okay. Yeah. Sounds good.
All
All
right.
right. Thank you.
Okay, take care. And that's all, folks. Thank you for listening. And week is spelled W-E-A-K. Just kidding.